Hi guys, and welcome to the beginning of Membranes and Transport, our Chapter 7 lecture. So we're going to break this into two parts. Today we're going to do membrane structure and passive transport. That will be part 1. So we need to take a look at the membrane. Now, as we talked about in macromolecules, the membrane is going to be mainly made of phospholipids, but there's a lot of other stuff in here that we need to take a look at and make sure we understand. So we need to make sure that we understand that it's going to be interconnected with the microfilaments of the cytoskeleton. Okay? I'll tell you what I can't do. We also need to make sure we understand that there's going to be cholesterol located within. Okay? That's going to be important for membrane fluidity down the road. We need to see that there are integral proteins, okay? Anything that's embedded within the membrane. And then there's peripheral proteins, which are on the side. We have some glycolipids, and we've got some glycoproteins. A lot of vocabulary in here. We need to make sure we know what these things do. And as we talked about in the last section, this is the fibers of the extracellular matrix, which are going to be connected to the membrane. So the plasma membrane serves as a barrier for the cell, keeping the inside environment separate from the outside environment. You can't do homeostasis if you don't have an environment that is going to be separate and distinct from the outside environment. Now, we know that the plasma membrane exhibits selective permeability, also known as semi-permeability, by closely monitoring substances traveling in and out of the cell. This is due to the phospholipid bilayer's its structure, okay? Membranes all throughout the cell behave in a similar manner. So in a cell, all the membrane is basically going to be composed of the same thing. So from the ER to the Golgi to the outer membrane, the cell membrane, it's all going to be the same. So let's talk about the constituents of the membrane. Plasma membrane is primarily composed of phospholipids and proteins that are amphipathic. We know that things that are amphipathic are going to be both hydrophilic and hydrophobic. Okay, so we know that the phosphate group and the choline in a phospholipid are going to be hydrophilic, and the hydrocarbon tails of the phospholipid are going to be hydrophobic, which is why the heads face the water and the tails face away from the water. But not only do the tails face away from the water, but they also face toward each other. So then this is unlike repelling, right? So hydrophilic is attracted to water, but hydrophobic repelling the water, but also like attracting like in that the hydrophobic tails are going to attract each other. So that both of those would be considered cohesive behavior. They're going to, if you just took a handful of phospholipids and chucked them into water, they would self-assemble into this structure. Now, early membrane models didn't account for the hydrophobic regions of proteins molecules. They didn't understand exactly how things were put together. If you go back to 1935, Davison and Dinelli, they just thought it was like a peanut butter and jelly sandwich. Okay, they didn't understand how that things were actually embedded. But in 1972, Nicholson and Singer proposed that membrane proteins are inserted into the phospholipid bilayer. So rather than being a peanut butter and jelly sandwich with the proteins on the inside, they're actually going to be more like a Jell-O mold with fruit shoved inside the Jell-O mold as part of the Jell-O mold. Now, how did they figure out that there was a fluid mosaic model? So what they actually did was something called freeze fracturing. And they took the plasma membrane and they cooled it down significantly so they could literally break it in half, okay? And when they did that, they saw the inside of the cytoplasmic layer had these little bumps, and that was because the proteins are actually embedded within them and they're sticking up out of one side and not the other. So the plasma membrane is a fluid structure with various proteins either embedded in or attached to the double layer of phospholipids. Okay? So if it's an embedded protein, it's an integrin. Okay? It's an integral protein. And if it's on the side attached to the double layer, then it's a peripheral protein. So how can it be fluid? The membrane is held together primarily by hydrophobic interactions. That's going to be hugely important. We briefly talked about that when we talked about the tertiary structure of proteins. Now we're going to see how that's going to happen between the tails. The molecules within a membrane are not locked in place and can move around. Phospholipids laterally move, okay? They drift by each other, okay? Sometimes they flip-flop, but that's rare, okay? And the proteins move or drift slowly, which makes sense because you're looking at their size in comparison with the phospholipids. They're much larger. Some are immobile, some can't move because they're attached to the cytoskeleton, okay? So lateral movement occurs 10 to the 7 times per second. That is a lot, okay? That's a significant amount. We're talking 10 million times per second. So a lot of that, very rarely do they flip, okay? They about once a month. About once a month. There was literally some dude's job that was to figure out how often do they do this. He must have been very excited when it happened that one time. Yes, they did it. All right, Steve, you're going to have to watch it for a year. Tell us how many times.
It happened 12 times.
Okay. Another way that they were able to determine that the membrane was fluid is they conducted experiments. Now, throughout the chapter, they throw these experiments in, and I think these are very important for you to take a look at, because they will throw these, the College Board will throw these on a test, and they'll be like, let's say we conducted this experiment. What would it show you? If you know that experiment ahead of time, it's going to be much easier for you. So they took a mouse cell and a human cell, and they combined them into something called a house. Just kidding, it's just a hybrid cell. But the reason they did this is because mouse cell proteins and human cell proteins, while similar, are also very easy to differentiate between each other. Okay? No, they're not colored pink and purple like they are in this visual, but it's as easy to determine the difference between them as it is by looking at these different colors. And what they saw is, after they created this hybrid cell, after about an hour, there was an equal distribution of proteins throughout the cell, which means the proteins were able to move beyond each other, okay, to intermingle with each other because the membrane is fluid. Now, the membrane is comprised primarily of lipids, and lipids are temperature reactive. We know that saturated fatty acids are solid at room temperature. We know that unsaturated are liquid at room temperature, but we all have played this game where you leave the butter out and it goes from solid to a liquid with a slight change in temperature. All right, we're not talking we have to heat this thing up in the oven. Just have a warm day in the summertime and you'll get a glob of butter. So we can see that phospholipids are going to need to interact, and we need to maintain a certain membrane fluidity. So you need to make sure you recognize that, like, membrane fluidity we don't want it to be too fluid and we don't want it to be too solid. So we can't get too warm or too cold. There needs to be a way of maintaining our membrane fluidity. Now, one of the ways that we can regulate our membrane fluidity is by changing the constituents that the membranes are made out of. So membranes can resist solidifying at lower temperatures due to the presence of unsaturated fatty acids that prevent tight packing. So let's say that you have an organism that's found in cold temperatures. You might find a significant amount of unsaturated fatty acids in the phospholipids, because that's going to allow them to be separated more from each other and not as tightly packed. If you're going to be an organism that's going to be in very warm temperatures, okay, so we'll do a comparison very quickly of fish. So a fish that would be found in a cold environment like the North Atlantic cod might have a membrane like this. A fish that's found in a tropical location like in the Bahamas might have a membrane like this. Because it's going to be very warm temperature there, you might have 80-degree water. You don't want the membrane to get too loose, so you've got saturated hydrocarbon tails. In the cold Atlantic, you don't want there to be too tightly packed, so you're going to have the unsaturated hydrocarbons. Now, animal cells have a cheat. Okay, they can use cholesterol. Cholesterol also counteracts temperature changes by maintaining normal fluidity. Okay, the higher the temperature, this is going to inhibit overdrifting, and the lower the temperature, it's going to inhibit solidification. So rather than having to change the structural makeup of the fatty acids within the membrane, we just have cholesterol embedded within, and that helps to maintain membrane fluidity. Now, membrane proteins. Various cells have different proteins depending on their function. Membrane within the cell also contain a variety of proteins for inner cell functions. So there are basic types of proteins, right? You're either a peripheral protein, which are not embedded, right? They bond to surfaces of the membrane or other proteins, or integral proteins, which penetrate hydrophobic regions, mostly transmembrane, okay? Which means they go all the way through. Transatlantic flights go across the Atlantic. Transmembrane proteins go across the membrane. Integral proteins are characterized by prominent alpha helices. Okay, so we talked about this. Again, there's a significant amount that are important about the folding of a particular protein. Make sure you recognize where the N-terminus and C-terminus are located. Okay, and recognize that the portion of the protein that's going to come in contact with the hydrophobic tails is itself going to be hydrophobic, and the portion of the protein that comes in contact with the water or the cytoplasm, it's going to be hydrophilic. How do you do that? R groups. Okay, keep that in mind. This is why these proteins must be amphipathic. So what kind of R groups would you have right up alongside the hydrophobic tails? Nonpolar R groups. And which kind of R groups would you have right up against the cytoplasm or the water here? Polar R groups, or electrically charged R groups. Proteins may be held in place by cytoskeleton and the ECM on either side of the membrane, so they're not necessarily always on the move. They could be immobile if they're connected to something. You need to make sure you know the protein functions. So there's transport proteins, right? A protein that spans the membrane could enable things to be able to move through the membrane. For example, this channel protein or this carrier protein can change shape and enable the molecules to get across the membrane. What kind of molecules? Well, what can't get past the hydrophobic tails? Polar molecules, charged molecules, ions, things of that nature. So we need these proteins embedded in the membrane to help move things. Enzymes. Sometimes we have enzymes that are needed for making reactions happen inside of the cells. So we embed them in the membrane so they're always there, and make sure you recognize that the active site must be toward the cytoplasm. Signal transduction proteins. A membrane protein may have a binding site with a specific shape that fits the shape of a chemical messenger such as a hormone. There may be a hormone that cannot get in because of the semi-permeability of the membrane. Well, how are we going to get that message in? Receptor proteins. Okay? In the same way that an enzyme has a specific active site, receptor proteins have a specific binding site for a particular signal and initiates a particular response inside the cell when that signal binds. Cell recognition. Some glycoproteins serve as identification tags that are specifically recognized by other cells. This is hugely important for which body system? Yep, the immune system. You need to be able to recognize self from non-self. What that means is you need to be able to recognize pathogen cells, okay, and distinguish them from non-pathogen cells, cells that are your body. You don't want the immune system to attack your body cells. Sometimes that happens. That could lead to an autoimmune disease. Occasionally, we need intercellular joining. Membrane proteins of adjacent cells may hook together in various kinds of junctions, such as gap junctions or tight junctions. So membrane proteins are involved in those. And then attachment to the cytoskeleton. You need a way to connect the cytoskeleton to the membrane because you may want to change the shape of the membrane. Why would you want to change the shape of the membrane? For example, pseudopodia. And if you can't connect the contracting parts of the cytoskeleton to the membrane in order to create the change, you won't get a change. So you need to have membrane proteins that are attached to the cytoskeleton in order for the pseudopodia to work and to get amoeboid motion. Other important molecules. Glycoproteins and glycolipids are critical for cell recognition. Cells recognize other cells by binding to these carbohydrates on the outside of the membrane. This is what gives blood type and its situation, right? Some people are like, oh, I'm O blood type. Okay, I'm the universal donor. Well, the reason for that is you don't have the carbohydrates on the outside of your red blood cells. So there's nothing to cause a problem. If O blood gets donated to A, it doesn't cause a problem. If O blood gets donated to B, it doesn't cause a problem. If O blood gets donated to AB, there's no reaction. Okay? If the body recognizes a protein, that glycoprotein with a carbohydrate that's not its own, it will initiate, okay, a response. There will be immune responses that will actually break down and cause agglutination, which could cause clots and kill you. So type O blood can only accept type O. If you try putting A in O, this guy has no carbohydrates. The A carbohydrates set off an immune response. The B carbohydrates set off an immune response. The AB at the same time set off a really intense immune response. You could die, you could die, you could die. People with O blood can only accept O blood. People with AB blood, give me O, no problem. There's no carbohydrate. Give me A. I have A. I recognize A. Give me B. I have B. I recognize B. Give me both A and B at the same time. That's who I am. I recognize that. I can accept all the blood. Okay? Now, this is just A and B. This has nothing to do with positive and negative. That's actually a different protein. Okay? We'll talk about that down the road when we get to blood type in inheritance. But this is what's actually occurring. There's actually glycoproteins on the outside of the red blood cells that are initiating, either they are initiating or not initiating a cellular response. All right, synthesis and sidedness. Proteins have a specific orientation in the membrane and are therefore packaged accordingly. So let's take a look at this protein out here. This is a glycoprotein, right? You see these green guys? Those are the carbohydrates, okay? You'll notice this when this secretory vesicle combines with the cell membrane, the glycoprotein has to be on the outside of the cell. when this becomes part of the cell membrane, okay, the inside of the secretory vesicle becomes the outside of the cell. We need to keep that in mind. From the creation of this protein until it gets to the cell membrane, we have to create that in mind. So, where are proteins created? They're created, they're created in the ER, okay? So when I make this protein in the ER, I've got to know exactly where this protein is going, okay? So this is a transmembrane glycoprotein that's going to go to the outside of the cell. What do? I have to make sure that the glyco part, the sugar part, is on the inside of the ER so that it can become the inside of the vesicle that transports it to the Golgi. So it could be on the inside lumen portion of the Golgi, so it can be on the inside of the secretory vesicle, so it can be on the outside of the cell. Okay? And so why is that important? The lumen side always stays the same and ends up becoming the outside of the cell, and the cytoplasmic side always stays the same. So the cytoplasmic side of this protein is the cytoplasmic side of this protein, is the cytoplasmic side of this protein, is the cytoplasmic side of this protein, which is embedded in the membrane. Okay? So you need to make sure you remember that. Selective permeability. The plasma membrane regulates the transport of substances in and out of the cell, right? The nutrients need to get in. Waste products must be removed. Substances for export need to get out, okay? So we need to make sure things can move through the cell. Some things can easily move through the membrane. Other things cannot. The membrane selectively allows molecules to pass a number of ways, often at different rates. So there's two main ways that you're going to move through the cell. Passive transport. Okay, substances move along a concentration gradient established on either side of the cell without using energy. So that's diffusion and facilitated diffusion. So we say no use of energy, no outside use of energy, no ATP. Okay, but you can still use the regular energy that's involved within molecules. So the kinetic energy that's in the molecules will drive diffusion. And then we have active transport. Active transport are substances that move against their concentration gradient with the input of energy. So transport pumps will be the proteins that will move those, and we'll also see that in exocytosis and endocytosis. Okay? All right, so passive transport. By definition, diffusion is the movement of molecules from a high concentration to a low concentration. Okay? They move down their concentration gradient. So there's more purple up here, less purple down here. They're just going to flow from where there is more to where there is less. That is simple diffusion. Simple diffusion, things can move through the membrane without any help. Facilitated diffusion, you're still moving from a high concentration to a low concentration, but you need the help of a protein to get through the membrane. Whereas ATP, if we take a look at what's happening here, okay, the orange squares are actually moving in this direction, okay? They're moving in this direction. They're going from a low concentration to a high concentration. They're moving against their concentration gradient, okay? And we can see the same thing happening with the orange balls. They're moving out, okay? They're moving out from a low concentration to a high concentration. And that requires energy. You're pushing things against their concentration gradient, okay? Now, what is diffusion? It's the tendency for molecules of any substance to spread out evenly in the available space. This is one of the important things that I want you to know. True or false? You need a membrane for diffusion. False. If you look at this visual right here, we dropped a solute like food coloring into a solvent like water, okay? There's no membrane of any kind. There's no cell. And yet we're still going to get diffusion of that molecule. It's going to dissolve, and it's going to disperse throughout the beaker until it's equally, right? It's all equal, until it's all equal. So you go from a high concentration to a low concentration until there is no concentration gradient and everything is equal. You do not need a membrane. Now, typically we will have a membrane with the cells, and that's why we're going to get this difference across the membrane, okay? So a concentration gradient is established when a substance in one area has a greater concentration as compared to another area. So we're looking at left and right. There's a lot of orange on the left, no orange on the right. There's a high concentration on the left, there's a low concentration on the right. Can't get lower than none. So the oranges want to go from the left to the right. Okay, they're going to move down their concentration gradient. Now, these are randomly moving. They're randomly walking using the energy that they have. Okay, and after a while, you may get one back, but the net movement of molecules is still going to be from the left to the right. There may be a guy that moves from the right to the left, but the molecules in general will move. So you get 3 guys going this way, 1 going this way, you still get a net movement of 2 until you reach equilibrium and there's the same number on either side. Now, does that mean it stops moving? Absolutely not, okay? In nature, we do not have what's known as the static equilibrium. We have a dynamic equilibrium. So we'll just get a 1-to-1, okay? One guy goes this way, one guy goes this way, and we maintain our balance. Different substances occupying the same area diffuse independently of each other. The purple balls don't care what the orange balls are doing. Everybody moves down their concentration gradient. So purple is going to go to the left, and orange is going to go to the right. Net diffusion of orange is this way because it's going down its concentration gradient. Net diffusion of the purple is going to the left because it's going down its concentration gradient till purple's even on either side and orange is even on either side. They move independently of each other. Solutes do not care about the concentrations of other solvents. So, simple diffusion. Molecules that are hydrophobic and small can dissolve in the lipid bilayer and cross the cell membrane easily. You should have illustrative examples. CO2 gas, O2 gas, and even water can move across the membrane easily through simple diffusion. Now, I know water is not hydrophobic, but it's very special and does whatever the hell it wants. Okay? It's small enough, and it's also ubiquitous. It doesn't matter. So these are great examples of what can move through the membrane by simple diffusion. Polar molecules such as glucose and water can also cross the cell membrane, but very slowly. And they may, in order to increase the speed that they move at, they may need a protein as well. Charged molecules? No. Okay? If they're surrounded by a large enough hydration shell, they can move really, really slowly. But again, if we're going to have a charged molecule, it would be good for us to have a way to get them through easily, which is why we have facilitated diffusion. Many polar molecules and ions that cannot directly dissolve in the lipid bilayer diffuse through the membranes with the help of transport proteins. That could be channel proteins, carrier proteins, or ion channels. So you need to be very specific in what you're doing and using them for. Keep in mind, in the same way that enzymes were substrate specific, transport proteins are going to be, they're going to be not substrate specific, but solute specific, molecule specific. A chloride ion channel will not move sodium molecules. All right, they're very, very specific for the ion they're going to move or the particle they're going to move. So channel proteins have hydrophilic passageways to allow molecules such as water or ions to pass easily through. So this area might be hydrophobic because it's kind of coming in contact with the tails, but this entire channel is going to be hydrophilic, which allows the ion to move through it. Okay? There are even specialized water channels called aquaporins that enable water to move at a high rate of speed through the membrane if we need to move a lot of water at once. Okay? And again, down its concentration gradient, this is facilitated diffusion. Carrier proteins bind specific substances that induce a modification in the protein's shape, which effectively transport molecules such as glucose across a membrane. I'm going to ask you this question. You should make sure you know it. What causes the change of shape of the carrier protein? Have an idea. Ion channels. A stimulus such as a change in membrane potential or other substances cause the channel to open. So in this particular case, there's a receptor area. Okay? A neurotransmitter chemical attaches to the receptor that opens the channel. And now we get movement. Sodium comes in, potassium comes out. And then that's going to be very important. If we have a voltage-gated ion channel, that's going to be, you need to change the voltage, which is going to be happening in something like a neuron where you're going to be dealing with charges like positives and negatives, and that would be what's going to change and open up a channel. This will make much more sense when we get to neurons down the road. All right, so osmosis. We can't talk about passive transport without talking about osmosis. Water is so special that it has its own name when it diffuses. When CO2 moves from high concentration to low concentration, it's just called diffusion. When oxygen moves from high concentration to low concentration, it's just called diffusion. When water does it, osmosis. Because it's so important. When a substance lacks the ability to move across the cell membrane, water will move until the concentrations of the solutes on both sides is equal. Sometimes water has to balance. Okay? Nature cannot deal when things are out of equilibrium. And sometimes things are not going to be able to move. They just can't because of a membrane in place. So water is going to have to do the job of balancing. Okay? Osmotic pressure is defined as more solutes equate to higher osmotic pressure. So more solutes is going to draw water. That's osmotic pressure. You're drawing the water in. The more solute, the more water you drag in, okay? Because it's trying to balance. So we can see if we count, there are more purple on the right-hand side here than on the left-hand side. That's what makes this a hypertonic solution. That's going to pull the water this way because what you're trying to do is you're trying to equal concentrations, okay? Think about it like a fraction. You're looking at the number of purple versus the number of water molecules. Well, there's more purple on this side, so therefore to create the same fraction, to create the same ratio, we need to have more water. So whatever the balanced number is of purple to water, it's going to be equivalent on the either side of this, okay, after the move. Okay, and that's why we've established an equilibrium. So let's just say it was one purple to 10, okay, and there's 6 on this side. Well, then I know that I have 60 water molecules on this side. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I know I have 130 water molecules over here because the ratio needs to be the same. Even though it looks odd, the ratio is the same, and so it's at equilibrium. All right. By the way, this is known as a U-tube. Okay, it's legitimately from science. It's a tube shaped like a U. It has nothing to do with videos. Okay, so we are going to see some U-tubes upcoming. Okay, and they're going to be used as a way of putting together a scenario where you're going to be asked what's happening. Okay, and you need to make sure you understand. So in this particular case, we've got a selectively permeable membrane. The membrane is permeable to water, but not to whatever the hell this substance is. So that's our solute. Okay, and so what ends up happening is the solution on the left-hand side has more solute than the solution on, the solution on the right-hand side has more solute than the solution on the left-hand side, so the water moves to the left. Now, scientists can't always say that sentence. It's too annoying. There's more solute over here and less solute over here. Just, we need terms to describe this. We need vocabulary, okay? So a cell is exposed to various solutions that may cause it to gain or lose water, a property called tonicity. Okay, tonicity is based upon solute concentrations. So we need to be looking at it from the perspective of the solute, not from the water. So we've got words to help us describe solutions. Okay, so solutions that are going to be surrounding a cell, and that could also be in a U-tube here. We may have solutions next to each other that we're going to compare to each other. We use these words. These are words for comparison. Isotonic, same concentration of solute, no net movement of water. So we're comparing two solutions. This could be on the inside and outside of a cell, or this could be both sides of a U-tube. Isotonic means they have the same amount of solute, so there's no movement of water. Okay? In this case, we see that these are not isotonic, right? There's clearly more solute on the right than there is on the left. So what word do we use there? Hypertonic. Okay? Now, hypertonic means there's more solute, and that means the water is going to leave the cell. Hypotonic, less solute, water enters the cell. Now remember, these are for comparison, okay? So there's more solute on the right, less solute on the left. When there's more solute, we're going to use the term hypertonic. Hyper meaning more of. If someone is hyperactive, they have a lot of activity. Hypo means low. So there is a less solute on this side, so this is hypotonic. Again, they're in comparison to each other, okay? Please remember, it's like using terms like faster and slower, okay? If I say my grandma is faster than what? I don't know. It doesn't make any sense unless I can compare, okay? My grandma is faster than molasses uphill in winter? Okay, not that fast. My grandma's faster than Usain Bolt? Fairly impressive. All right, you need to be able to compare them to something. So in this particular case, when you're using hypertonic, you need to know what you're comparing it to. You just can't look at the solute concentration and say, there's 10. This is hypertonic. Nah, it's not hypertonic unless it's compared to something that has less than 10. All right, so keep those words in mind. When you're putting typical cells in these solutions, they're going to have a response. So when we take an animal cell and place it in a hypertonic solution, that means that there is more solute outside, less solute inside. Water is always going to be attracted to where there's more solute. So if it's in a hypertonic solution, there's more solute outside, the water's going to leave. And the cell will become shriveled. Okay? This happens to both plant and animal cells. In a plant cell, it's known as plasmolysis because the plasma membrane pulls away from the cell wall and creates this funky-looking plant cell. It's unhappy. Neither one of these cells are happy, but they're gonna not like this situation. Isotonic solution. Okay? This is a normal cell, just having a good time. Water goes in, water goes out at a 1-to-1 situation. This is fine, okay? This is a flaccid cell. Plants don't really like being in an isotonic solution. They'd much rather be in a hypotonic solution where water is going in because they have an advantage, okay? Take these two cells. Now, I know in this visual, this cell just looks like it's hairy, okay? But this is actually exploding. Why? So much water has moved in that this cell went boop. It exploded. It underwent cytolysis. It lysed. That's very bad. The plant cell, on the other hand, chilling. Okay, no problem. Look at me. I'm having a great time. I can't explode. Why can't I explode? Why didn't it explode? Because it's got a cell wall. That is the advantage. Okay, that's the advantage of having a cell wall. You can't explode. Okay, explode, no explode. Explode, no explode. Okay, you need to make sure you can identify these. What happens if I flip the picture? Oh my God, this guy's exploding now. Get out of here. Go away. Oh, dear sweet Moses. We're fine. Don't come over here. All right, so this cell has exploded because the water came in. This cell is turgid, rigid, erect. It's actually very happy with its structural component. If it were to lose water and become flaccid, it would start to wilt and lose its structure. Okay, the red blood cell, totally fine with that. This guy, not so much. Put it in a hypertonic solution. This cell is going to shrivel. This cell is going to be plasmolyzed. So nobody likes hypertonic solutions. Only this guy likes hypotonic solutions, and people are okay in isotonic solutions. So keep an eye on that. Here's an Elodea cell in a turgid normal state, maintaining its structure, being very happy. Okay, here's an Elodea cell in salt water experiencing cytolysis. You'll notice that this is the outside cell wall. This is the cell in comparison. It usually fills the entire space. It has pulled in significantly, and it is experiencing plasmolysis, and it is very not happy. All right. We're going to do active transport next. Make sure that you look everything over. If you've got questions, let me know.